Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 14th video lecture. And unlike our last lecture, Lecture 13, where I only did one theorem, today we're going to look at 5 theorems having to do with Riemann-Stieltjes disintegration. 4 of those theorems I will prove, and one of them I'm going to leave as a homework problem for you guys to do. As a matter of fact, that theorem, the one whose proof will be left for you, is the first thing that we're going to mention. Before I get started with that, let me say that these are theorems about Riemann-Stieltjes disintegration, and they will primarily, the latter part of this lecture, deal with where we talk about the alpha and some kind of algebraic properties of them. Okay. So here's the first theorem. If f sub 1 and f sub 2 are elements of Riemann-Stieltjes integral functions with respect to alpha on a to b, with f sub 1 of x being less than or equal to f sub 2 of x for all x element of a to b, then the integral from a to b of f sub 1 d alpha will be less than or equal to the integral from a to b of f sub 2 d alpha. Proof is going to be a homework problem. And it's easy. You can do it. So that's what we'll start off with today. The second theorem, and the remaining 4 theorems, we will prove, I will prove here. The next theorem says the following. If f is a Riemann-Stieltjes integral function on a to b, and if a is less than c is less than b, then f is Riemann integral with respect to alpha on a to c and separately on c to b. And moreover, the integral from a to c of f d alpha plus the integral from c to b of f d alpha, well, that's going to be equal to the integral from a to b of f d alpha. So this is a theorem that we would have in calculus about Riemann integration. Here we're talking about Riemann-Stieltjes disintegration, and we're going to prove this. So we're going to let f be Riemann-Stieltjes integral. Here I need to be very careful, so we're going to be talking about on a to b. So I need to be careful about not only the Riemann-Stieltjes disintegration, we need to be careful, but also on what integral we're talking about. And we're going to let a be less than c be less than b. Well, we're going to use that main theorem when we talk about proving that f is Riemann-Stieltjes integral on a to c or from c to b. That main theorem that I'm referring to is the one that says that's going to happen if and only if, given any epsilon greater than 0, there's that partition of either a to c or in the second case from c to b. So 2 separate partitions what we're going to come up with here. Such that the upper sum with that partition minus the lower sum of that partition be less than epsilon. So that's what we're going to use. We've been using all of them here. So we got a is less than c is less than b. We're going to let epsilon be greater than 0 be given. So get to that theorem. Okay. Since F is an element of Riemann integral function with respect to alpha on A to B, that means by our important theorem, there exists a partition of A to B such that the upper sum, we're talking about with integral A to B, with this partition F and alpha minus the lower sum with this integral A to B with this partition F and alpha will be less than anything we want. We're going to say epsilon. Now consider a refinement of P. We're going to call it P star, which is equal to P union the one number C. Now, C might already be in P, I don't know. But if it's not, we're joining it. Then, when we look at this upper sum, from A to B, with P star, F, and alpha, minus this lower sum, A to B, with P star, F, and alpha, that's going to be equal to the sum as I run from 1 to n of m sub I minus little m sub I times delta alpha sub I. That's the definition, that comes from the definition of this upper and lower sum. You know, this B needs to be closed. Okay. Now what we're going to do is suppose C is equal to, I'm going to call it x sub j, which is an element of P star, that partition. So I'm going to label C as x sub j. Now, the sum, as I run from 1 to j, of m sub I minus little m sub I, delta alpha sub I, of course that's going to be less than or equal to this, let me write it down here. It's going to be less than or equal to this upper sum over A to B of this partition, P star, F and alpha, minus this lower sum over this A to B, P star, F and alpha. The reason that's true is that this is part of this subtraction, but not all. And each guy involved in the sum that's not included in here, that's in here, is positive. So that part here is going to be bigger. Okay. So, if we then look at P star and we just reduce it from A to C, and this is going to be equal to x sub 0 all the way up to x sub j. That's contained in P star, and what I mean by P star, that's the one that is the partition of A to B. Okay? And this P star of A to C is a partition of A to C. Okay? And what we have is that this upper sum from A to B, I'm sorry, I'm going to say from A to C. No, I'm going to write it this way. Upper sum of the partition star from A to C with F and alpha minus this lower sum with the same partition P star from A to C, that A loops picked, with F and alpha. Well, that's this guy right here, okay, is less than this guy. So I'm going to write that down. It's less than okay, look, this is an upper sum minus a lower sum right here. And to show that F is Riemann integral from A to C with respect to alpha, Riemann-Stieltjes integral, what I need to find is one of these partitions such that the upper sum minus the lower sum with that partition is less than epsilon. But what I've got is, for this partition, this subtraction, upper sum minus the lower sum, which is this, is going to be less than this. That's what I'm going to write next. I'll say less than or equal to. The upper sum over A to B of P star, so that's the partition over A to B, F alpha minus the lower sum from A to B with this partition F and alpha. And we know that to be less than epsilon because F itself was integral, Riemann-Stieltjes integral with respect to alpha over A to B. So that's how we came up with this partition. P star, essentially it's P, but we added something to it to C. So it still has that property, it's less than epsilon. And so, what that says, in considering the first part of that inequality that I've written, we come up with this partition up on A to C. We call it P star sub AC, such that the upper sum of that partition minus the lower sum of that partition is less than epsilon. And so by our theorem we're using over and over to show Riemann-Stieltjes integrability, we have that F is Riemann-Stieltjes integrable on A to C. All right, that's part of the theorem. Similarly, the sum as I runs from J plus 1 to N of M sub I minus little m sub I times delta alpha sub I will be less than or equal to the sum I run from 1 to N of M sub I minus little m sub I delta alpha sub I. And of course that's nothing more than the upper sum A to B of this partition star with F and alpha minus the lower sum. That's what that's last sum that's here. Minus the lower sum, A to B again, with this partition star F and alpha. And of course we know that's less than epsilon. Okay? So this guy is less than epsilon. But what is that guy? Using the same notation as what we had previous part of the proof. We let P sub, let's say C to B be equal to, so here it will be x sub j plus 1, all the way up to x sub n. Okay? Let's call it star here. Then this P sub C to D star is a partition of A to B. Okay? Well, we're thinking of these points as being in P star, which is the partition of A to B. Okay? So, then, if you will, the upper sum with P star from, I'm going to write it from, this isn't a partition from A to B, it's a partition from C to B. Okay? From C to B, F alpha minus the lower sum, and this P star from C to B, F alpha, that's going to be equal to, well, it's the sum, what we've already looked at over here, it's the sum as I run from j plus 1 to n of m sub I minus little m sub I times delta alpha sub I, which we know to be less than or equal to, or less than, epsilon. So that says F is Riemann-Stieltjes integrable with respect to alpha on, and this will be C to B. So we've got part of what we wanted to show for this theorem, and now we need to show that the addition of these integrals will equal to the integration over A to B of F. Okay. Now, if you take the upper sum with P, F, alpha, let's call this P from A to C, plus an upper sum with P over B to C, F and alpha, that will be equal to, I didn't write this correctly, this should be C to B. That will be equal to the upper sum with the partition that's formed from the union of these two guys, which I'll just call the partition from A to B with F and alpha. Okay? The union of those guys. And I can say the same thing with the lower sum. So this is kind of notationally giving us some representations. P from A to C, F alpha. I don't know why I put brackets. That should be parentheses. Plus this lower sum, P from C to B, F and alpha. That can be thought of as the lower sum from a partition from A to B with F and alpha. They'd be the same. Okay. So here's some information, some facts having to do with infiniums then. And so here, if, looking at this inequality, this top, what we have is the infinium of this guy over all partitions of the form A to C, of this partition A to C, F alpha, plus the infimum over all partitions from A to C of upper sums. No, I don't want A to C. I want C to B. Upper sums with the partitions from C to B, F and alpha. Okay, that's going to be less than, I'll write right down here, less than or equal to the infimum over all partitions from A to B. A to B, I said. Of that type of partition, A to B, F, and alpha. Now, what that'll tell us is that the integral, because of those infimum properties, the integral from A to C of F, d alpha, that's that first infimum involved in the previous statement, plus the C to B of F d alpha. That's going to be less than or equal to the integral from A to C of F d alpha. So we want to show these two quantities are equal. And what we got is a less than or equal to. So we need to show the other direction of inequality to prove equality. Well, we'll be able to do that similarly by looking, instead of the upper sums, let's look at the lower sums. So also the sup over all partitions of A to C of, here's the lower sum, partition of A to C, F alpha, plus the sup over all partitions from C to B of lower sums involving partitions from C to B of F and alpha. Well, that part is going to be greater than or equal to, the sup over all partitions from A to B of lower sums involving partitions from A to B of F and alpha. So that statement gives us, this was nothing more than the integral from A to C of F d alpha plus, that here is the integral from C to B of F d alpha, and that's going to be greater than or equal to this part, which is nothing more than the integral from A to B of F d alpha. Here, I think I made a mistake. This right here should have been from A to B. I made a mistake in reading what I had written before. Make that change. That's what this should be. Now look, if you look at these two inequalities, what they mean is, because the left-hand side is less than or equal to the right-hand side in one statement, and the left-hand side is bigger than or equal to the right-hand side in another statement, the only way that can happen is if they're the same. So that's what I'm going to write out. So that tells me that the integral from A to C of f d alpha plus the integral from C to B of f d alpha is equal to the integral from A to B of f d alpha. That concludes that proof. Here's another theorem. If f is Riemann-Stieltjes integrable with respect to alpha on A to B, and if the absolute value of f of x is less than or equal to a number m on A to B, then the integral from A to B of f d alpha will be less than or equal to m times alpha of b minus alpha of a. Oops. That's what we want to prove. Okay. So the way that we're going to prove this is to show that the absolute value of a number is less than or equal to this other number. What we're going to have to do is, of course this is positive, we're going to show that the integral from f to d alpha, not the absolute value, but the integral, just the integral of f of d alpha is less than this number, but yet bigger than minus that number. That's what we want to show. That's what we will show. Here's the proof. We'll start off with letting f be Riemann-Stieltjes integral with respect to alpha on A to B. And we're going to let the absolute value of f of x be less than or equal to m. On A to B. So here, let's observe this. Note, the integral from A to B of f d alpha. I know that is it. Well, that's going to be less than or equal to all the upper sums, of any partition you give me, f of alpha. Okay. Why do I know that? Because this guy is the infimum over all partitions of these upper sums. And this is going to be less than or equal to, this upper sum is going to be less than or equal to the sum. Remember what it has, this is mi's, where mi's are the supremum, yes, the supremum over the subintervals, x of I minus 1 to x of I. But here, this is what I'm going to replace that supremum, which I'm denoting by m sub I in our notation, I'm going to replace that with m, and that makes it bigger, so this m. Times delta alpha sub I, and that's equal to this big M times the delta alpha sub I. But these delta alpha sub I, they will have cancellations that occur throughout this sum, and what they'll yield is just M times alpha of B minus alpha of A. Okay? So we have that the integral from A to B of f d alpha is less than or equal to m times alpha of b minus alpha of a. All right, so we got to get a different inequality here. Very easily to get. Also, the lower sum with any partition of F and alpha, that's going to be less than or equal to the integral from A to B of F d alpha, like that. It's because, remember, this is defined to be the soup of all these types of numbers. Okay? And so that's going to be bigger than or equal to any one of them. Okay? Now note, this guy right here, that is going to be equal to, so I'm going to be a little bit more detailed than I was before. I running from, I won't write down the sum. It's just a little m sub i's, delta alpha sub i's. It's I running from 1 to n. But that's going to be bigger than or equal to, okay, so bigger than or equal to minus m delta alpha sub I. Okay. So I'm replacing the m sub i's, which are the infimums over the subintegrals created by the partition, by something that's less than or equal to it every time over the whole A to B. So I get this inequality. And that is going to be, this part right here is equal to minus m sum of the delta alpha sub i's. We've already seen what that is. That's equal to minus m, that's a big M there, and this is alpha of B minus alpha of A. And so, what we just found out is that minus m times alpha of B minus alpha of A is going to be less than or equal to the integral from A to B of F d alpha. So, combine that inequality with the inequality we had on the other side of the board, we have this. Minus m times alpha of B minus alpha of A is less than or equal to the integral from A to B of F d alpha, which is less than or equal to big M, yeah, that's beautiful, big M alpha of A, I'm sorry, B minus alpha of A. And so that says that the absolute value from A to B of F d alpha is going to be less than or equal to M times alpha of B minus alpha of A. And that's what we're going to prove, so that ends this theorem. Okay, I'd like to do two more theorems. And we'll call it quits. Here's the next and last theorem for today. It says, the last two theorems, they have to do with things about alpha and Riemann integrability. So here it says, if F is Riemann integrable with respect to alpha sub 1, and F is Riemann integrable with respect to alpha sub 2, then F is Riemann integrable with respect to alpha sub 1 plus alpha sub 2, and integral from A to B of F of B alpha sub 1 plus alpha sub 2, this is an A, will be equal to the integral from A to B of F d alpha sub 1 plus the integral from A to B F d alpha sub 2. We had an analogous statement to this in our last lecture, lecture 12, I should say, where we only did one theorem. That was analogous part of that theorem was
about F being, F sub 1, F sub 2. Here we've got alpha sub 1, alpha sub 2. Well, let's look at the proof. Here, if we let F be Riemann integrable with respect to alpha sub 1 and let F be Riemann integrable with respect to alpha sub 2. So the first thing we'll say note for any partition of A to B. Okay. Now the A to B isn't changing here. That's what we're talking about, A to B. The first thing I want to tell you is that you look at the upper sum. So the upper sum with respect to that partition, F and alpha sub 1 plus alpha sub 2. Well, what that's going to be equal to is the sum as I runs from 1 to n, some number. Here it would be the big M sub i's, and then we have the change in alpha sub 1 plus alpha sub 2. Let's continue to look at that. What that's going to be equal to, it's going to be equal to the sum as I runs from 1 to n of M sub I. Well, it would be times alpha sub 1 plus alpha sub 2 acting on, it will be x sub I minus alpha sub 1 plus alpha sub 2 acting on x sub I minus 1, which is equal to, this could be broken up into two sums. The sum as I runs from 1 to n. Here, this will be M sub I. This is going to be alpha acting on x sub 1 plus alpha sub 2 acting on x sub I, minus alpha sub 1 acting on x sub I minus 1, minus alpha sub 2 acting on x sub I minus 1. And we can split that up into M sub I times alpha sub 1 acting on x sub 1 minus alpha sub 2 acting on, I say alpha sub 1. Let's do it this way. Yeah. Acting on, this is x sub I. This is x sub I minus 1. I don't want to. And then, let's put that in parentheses. And then it would be plus alpha sub 2 acting on x sub I minus alpha sub 2 acting on x sub I minus 1. I think I'm being a little bit too careful here. So it's m times all that. So it's m times this guy plus m times this guy. You're summing those up. So we break those up into two sums. M sub I. Here it's alpha sub 1 acting on x sub I minus alpha sub 1 acting on x sub I minus 1 plus this sum as I runs from 1 to n of m sub I, and here this will be alpha sub 2 x sub I minus alpha sub 2 x sub I minus 1. And what this is the upper sum with any partition, the partition we're using, F, and here is just alpha sub 1. And this is plus the upper sum with the partition we're using, F and alpha sub 2. So that's what we get. Well, if I can do that with the upper sums, I can do it with the lower sums too. And so I'm just going to state that. So similarly, the lower sums, P, F, and alpha sub 1 plus alpha sub 2 will be equal to the sum of the lower sums. So P alpha, alpha sub 1 plus the lower sum with P, F, and alpha sub 2. That's equal. Okay. Now, we're going to let epsilon be greater than 0 be given. We're going to use that same important theorem about integrability with having a partition such that the upper sum of that partition minus the lower sum of that partition will be less than epsilon, where epsilon is any positive number that can give it to us. So since F is Riemann integrable with respect to alpha sub 1, and F is Riemann integrable with respect to alpha sub 2, then there exists partitions P1 and P2 of, I'll say of A to B, both of them, partitions of A to B, such that, and to save some writing, I'm going to employ a notation that we've used before in some sense. The upper sum with P sub I, before I call it J, let's just call it I, F, and then alpha sub I minus the lower sum with P sub I, F, and alpha sub I. That's going to be less than epsilon over 2. Epsilon over 2, that's what we got. Okay? Excuse me for a second. Less than epsilon over 2. And similarly, no, not similarly. We're going to let P star be equal to P1 union P2. So that's the common refinement. And then what we'll have is that the upper sum with the common refinement of F and alpha sub I minus the lower sum with the common refinement F and alpha sub I, so 1 or 2 here, doesn't matter, will both be less than epsilon over 2. Okay. So, upper sum, P star, F, and alpha sub 1, plus upper sum, P star, F, and alpha sub 2, minus the lower sum of P star, F, and alpha sub 1, minus the lower sum with P star, F, and alpha sub 2. That quantity. Now, we know that this is going to be less than epsilon. And the reason is this guy minus this guy is less than epsilon over 2. This guy minus this guy is less than epsilon over 2. But wait a minute. This first addition of the upper sums, that's nothing more than the upper sums with respect to alpha sub 1 plus alpha sub 2 minus this right here, the lower sum combination here is the lower sums with P star, F, and alpha sub 1 plus alpha sub 2. That's a fact that we did it within this theorem. Okay, something we've already proven. And like I said, we know that this is less than epsilon. So that means that F is Riemann, still just integrable, with respect to alpha sub 1 plus alpha sub 2. Now, since first sum with any partition PF alpha sub 1 plus alpha sub 2 is equal to the lower sum for the partition F alpha sub 1 plus lower sum partition F alpha sub 2, then this guy, the infimum of this guy is going to be less than or equal to, I'm sorry, I said the wrong thing. The supremum of this guy is going to be less than or equal to the supremum of each one of these added together. And so that means the integral from a to b of f d alpha sub 1 plus alpha sub 2 is going to be less than or equal to the integral from a to b of f d alpha sub 1 plus the integral from a to b of f d alpha sub 2.
Okay. Got a similar statement we can make.
So since the upper sum with any partition alpha sub 1 plus alpha sub 2 is equal to the upper sum PF alpha sub 1 plus the upper sum of PF alpha sub 2, then I'm going to take infimums. So that means that the infimum of this guy is going to be bigger than or equal to the infimum of each one of these. So that says that the integral from a to b of f d alpha sub 1 plus alpha sub 2 is going to be greater than or equal to the integral from a to b of f of d alpha sub 1 plus the integral from a to b of f d alpha sub 2. Okay? And so we have inequalities involving this integral and these other sums of these integrals in both directions. So that means those two things must be equal to each other. And that's what we wanted to prove. Okay, so that ends this theorem. All right, let's see what time it is. Okay, all right, we got time to go over time and do this last theorem. I will. I know it's a shock that I'm going to go over 50 minutes in the lecture. So here's the last theorem I want to do. It says if f is Riemann's integral with respect to alpha, and in this case we have to have c being bigger than 0, then f is Riemann integral with respect to c times alpha, and the integral from a to b of f times d of c times alpha will be equal to the integral from a to b of, well, I'll pull out the c of f of d alpha. Okay. So here's the proof. Again, we're going to use that important theorem to establish integrability of f with respect to c times alpha. That is, we're going to let epsilon be greater than 0 be given, and we'll be searching for some partition, such that the upper sum of that partition minus the lower sum of that partition is less than epsilon. Okay. First of all, if you just let P be a partition of A to B, okay, then let's look at that upper sum. with F, P, I'm sorry, I didn't write this right. With P, and then F and C alpha, that's going to be equal to the sum of the M sub i's, big M sub i's, with delta C alpha sub I. Here again, I running from 1 to n, so.
Now, what's that going to be equal to?
Well, that's going to be equal to the sum as I runs from 1 to n of big M sub I, and then this would be C alpha sub C alpha acting on x sub I minus C alpha acting on x sub I minus 1. You can factor out C, I will, that C times the sum as I runs from 1 to n of M sub I times alpha x sub I minus alpha x sub I minus 1. And that's what we got. And then that's equal to C, that last summation is nothing more than the upper sum with the partition F and just alpha. Okay. So similarly, I do the same thing with the lower sums. And what we have is that the lower sum with any partition F and C alpha will be equal to C times the lower sum with that partition F and alpha. Okay, now since F is Riemann integrable with respect to alpha, then there exists a partition, P sub 1, of A to B, such that the upper sum with P sub 1, F, and this is just with alpha, minus the lower sum with P sub 1, F, and alpha. Alright, so I can make that be smaller than any positive number that I want, and I'm going to say that's less than epsilon over C. Now look, that's why we have to have C being positive. Epsilon is greater than 0. If C is not greater than 0, this epsilon over C isn't necessarily greater than 0. So we have trouble finishing the proof. That's why we need that C being positive. How much more? Okay. So, C times this upper sum with P1, F, and alpha minus C times L with this upper sum, L with this partition, F and alpha, okay, will be less than epsilon. But what is this? Well, this is nothing more than the upper sum with P sub 1, F, and I can bring that C inside, that's what we've proven, and that's alpha, minus lower sum with this partition, F and C sub alpha. That would be less than epsilon. And so that establishes F being Riemann-Stieltjes integrable with respect to C alpha. Okay, now we've got to show the ending relationship that we want about the integrals. So here's what we say. Since C times this upper sum, P sub 1, F, and alpha, minus C times this lower sum, P sub 1, F, and alpha, is less than epsilon, then what we get is the integral from A to B of F with respect to alpha, I'm writing. C alpha, that's what I'm writing. This sum is less than or equal to the upper sum with P sub 1 F C alpha, okay, which equals to, okay, this is just a straight fact, okay, that this is true. But this guy is equal to the upper sum with P sub 1, no, it's equal to C times the upper sum of P sub 1 F alpha. Which is less than epsilon plus C times the lower sum with P sub 1 F and alpha, which is less than epsilon plus the sup of overall P's, if you will, of C lower sums P sub 1 F, well, let's write down P, F alpha. Okay. And you pull out that C, and this is going to be equal to epsilon plus C times the sup over all partitions of this lower sum of with P, F, and alpha. And that's equal to epsilon plus C times the integral from A to B of F d alpha. And so what that establishes is that the integral from A to B of F times D alpha, dC alpha is going to be less than or equal to C times the integral from A to B of F d alpha. Okay, so I've got one part of the inequality. I need to get the other part to show that they're equal. Also, since C times the upper sum P1 F and alpha minus C times the lower sum of P1 F and alpha is less than epsilon, then what we'll get is the integral from A to B of F d C alpha is going to be greater than or equal to the lower sum, we know this, of P1 F C alpha, okay, which is equal to C times the lower sum of P1 F and alpha, which is going to be greater than C, I'm looking here at this inequality, times the upper sum of P1 F alpha, and then it will be minus epsilon. Okay. So that means this integral from A to B of F d C alpha is going to be greater than the infimum over all partitions of this union, this upper sum, P1 F alpha minus this epsilon, which equals to C, this should have had a C with it. I made a mistake. And this is going to be C times the infimum over all these partitions of the union of P, F, alpha minus epsilon, and that's equal to C. This is the integral from A to B of F d alpha minus epsilon. We are almost through. So that says So that says that the integral from A to B of F dc alpha is going to be greater than or equal to C times the integral from A to B of F d alpha. So that means the integral from A to B combined the two inequalities of F d C alpha is equal to C times the integral from A to B of F d alpha. That ends this theorem and also ends this lecture. Thank you very much for your time and patience.